All right, so let's officially start. Hello, everyone. My name is Pavel. I'm the CEO and founder of the Quantum AI Foundation, which is a legal entity organizing this workshop. And I'm also the chairperson of the board of QWorld, which is an international organization aiming to build the global open ecosystem for quantum technologies. And in QWorld, we develop the educational materials on quantum computing, and this workshop will be based on these materials developed within QWorld by researchers from all over the world. And in particular, in QWorld, we have currently more than 30 local Q cousins, and QPoland is one of them. Actually, QPoland was one of the founding cousins of QWorld. And as QPoland, we organized this quantum computing workshop for you. This is already our 7th introductory level workshop we organized as QWorld, but as you can see, as QPoland, but as you can see, as QWorld, we've already organized more than 130 QBronze workshops. So a bit more about the workshop first, and then I will give a voice to our instructor. So there are 5 days of classes. We are starting today, and there will be 4 more days, so until Friday. Every day will start at the same time at 6 p.m. UTC +2, which is the time zone here in Warsaw now. Our main instructor is Krzysztof Kuba. Krzysztof, can you maybe say a few words about yourself?
Yes, hi, my name is Krzysztof. You can call me Chris for simplicity. I'm the student at the University of Warsaw at the Faculty of Physics, and I study nanoengineering, and I'm the member of QPoland for about 2 years. And I really enjoy quantum computing, and I'm looking forward to teach you something during this lectures, and I hope you will learn something useful and gain some more knowledge in the area of quantum computing.
Great, thank you, Krzysztof. So Krzysztof will lead the workshop for you, and we'll also have a few mentors. So here I apologize because it seems that I did some almost last minute additions, and I listed only one mentor, Przemysław Michałowski. I'm not sure if Przemek is with us. Przemek, are you with us maybe? If not, then we have a few other mentors. So you can find their names on the website of the event and on our Discord. And later I will update the slides once again and share the updated slides on Discord. So we also have Konrad Łącki. So Konrad, maybe you can also unmute and briefly introduce yourself.
Oh yeah, hello, I'm Konrad, and currently I'm studying in the Warsaw University of Technology, doing electrical engineering and applied physics, and I've been interested in quantum computing for about 2 years now. This is my second time being a mentor, so if you'll ever have any questions, please let me know, and I'll try to get back to you. Yeah, I hope you have fun during the workshop.
Great, thank you, Konrad. We also have Martyna. I'm not sure if Martyna is with us actually. Let me just check on the list. No, Martyna is not here on Zoom, unfortunately, but I know that she's active on our Discord. And there's also one more mentor, Maya, but I think she's also not with us. But they will also support you on Discord. So all the graphics that were used for promotion were prepared by Agnieszka Wolska, who's a member of the Q marketing department of QWorld. So we also thank her for doing this for us. And the workshop will be based on the so-called bronze materials prepared by QWorld, as I said, and this is the introductory level workshop, which means that you really learn the basics of quantum computing. As you probably read in the email that we sent to you, the only requirements are the knowledge, some basic knowledge of Python programming and linear algebra. So that's why this workshop is relatively accessible, and we know that we also have even high school students among the participants, which is great. All the lectures will be on Zoom every day. Maybe also use Discord, but currently we do not have it in our plans. There is an option to have video meetings on Discord as well. So this will be our backup option if something goes wrong. But the default option is Zoom. But communication with mentors, or the preferred way of communication with mentors is on Discord. The only exception is are the questions during the lectures. So then you can just ask your questions on the chat of the Zoom. So it could be easier, especially to the instructor, to open the chat than to just turn off the full screen mode and open the Discord. An important thing is that you can receive a certificate. You can receive a certificate, and in order to do it, you have to do your work. You have to do your homeworks. And there will be 5 homeworks. Each one will be released after each of the 5 lecture sessions. So the first one will be released to you just after this first lecture. And actually, I can even try to send you invitations a bit earlier. So just after my lecture, we use a specific platform to do the homeworks. This platform is called Canvas, and there are just some assignments for you. And as far as I remember, we've set to have 3 trials, and the maximum score from these trials will count. In order to get a certificate, you must get at least 50% of the points for homeworks. From each homework, and at least 70% of general points, so in total. The deadline for completing all homework sets in Canvas to receive a certificate is Sunday, October 13th, just before 10 p.m. Warsaw time. Okay, so this is these are just the most important information about the organization of this workshop. Since you have already joined our Discord, you can see that there are some dedicated thematic channels where you can also ask your questions, and our mentors are here to help you and answer your questions. Maybe just a few words about QPoland and the Quantum AI Foundation. So as I said, QWorld is this global network, global organization. So formally, there is an association, QWorld Association, that's registered in Estonia. But actually, QWorld is really a global network of individual groups and communities collaborating on education and implementation of quantum technologies and research activities. So in particular, we work together globally to prepare educational materials, and then we organize local workshops for our local communities, as we do here in Poland. But since this is an online event and we have space, we have capacity, then of course we also accepted the registrations and participants from other countries as well, which may also help us in building this global ecosystem, global community of quantum computing enthusiasts and later professionals, hopefully. And if you are from abroad, or if you are from Poland, feel free to reach us out later and join QPoland. If you are from other countries, feel free to reach us out to join or one of the Q cousins in other countries, or establish a new Q cousin in your country if there's no Q cousin in your geographical area yet. Besides these educational activities, we also organize some research activities like Q-Intern program, which is a program of online internships where we match researchers from all over the world with students, PhD students, or young researchers from all over the world who just can collaborate first during the several weeks of the summer. And if everything goes well, then they can continue their collaboration outside of the Q-Intern program. Yeah, and here are just some useful links. So I will later share the slides with you on Discord, so don't worry. You can follow our social media, subscribe to our YouTube channel, or join the Keywords Discord to stay up to date and learn about some other projects and some other events that we organize. So just to let you know, because we haven't announced it formally yet, but next week on Monday, we'll start the Q-Nickel, which is intermediate level workshop organized by Qword, so it could be already a follow-up for you. So we'll start announcing the QNICEL probably later today. We also organize hackathons, and at the end of October, there will be also an online hackathon that we'll organize as QPoland and Quantum AI Foundation. So you can already participate and test your skills, test the knowledge that you've gained, and collaborate, work with other people from all over the world on some interesting projects. And there will be several dedicated thematic tracks this year. I've already told you about this QIntern program and Q Research department in general, where QIntern is is just a part of Q Research. And I've told you that we develop these educational materials together. This is a global effort, global collaboration to do it, because in many countries there are still not that many specialists, experts, researchers in quantum computing to ensure that they can really prepare high quality training materials. So that's why it's better to collaborate globally, especially in underdeveloped countries. And eventually we would like to prepare the full curriculum of quantum computing, something like a quantum massive open online course, quantum semester. We've already had some trial versions of such longer courses. I've already told you about QPoland, so this is also a subpage of QPoland on the QWorld's website. There are also some useful links, and you can also join our mailing list or follow our profiles. And a bit more about Fundacja Quantum AI or Quantum AI Foundation. It is a non-profit organization established, registered here in Poland. I'm the founder and I'm currently the CEO of this foundation. And our goal is to support education, research, and cooperation in the field of science and new technologies, especially artificial intelligence and quantum computing. And this is formally a legal body behind this workshop. I can see that Maya, one of our mentors, is now joining. And in addition to the workshop, we also organize many other events like meetings or meetups of the Warsaw Quantum Computing Group. We also organize hackathons, contests, conferences. So you can also follow our profiles to stay up to date. All right, that's all from my side. If you have any questions, you can reach me out on Discord or by email. And with this, I would like to wish you a great experience with this workshop. I hope you will enjoy it and you will learn more and have fun in this process, of course. And if you have any questions now, then I will be happy to answer. And if not, then I will give the voice to Krzysztof.
Do mentors will be accessible up till the 13th of October or just
Yes.
along 5 days?
No, the mentor should be available on Discord also later, so until October 13th.
Thank you.
Okay. Any more questions? Okay, good. So I will now stop sharing the screen. Chris, if you are ready, the Zoom is yours, and I will maybe first. I'm not sure if the option to share the screen is enabled now. Are you able to share your slides, maybe?
I will try to.
Mm-hmm.
I'll send request.
Okay.
Okay, I will now try to share my notes, which I will be drawing here. Can you see them?
Yes.
Okay, thank you. Yes, as I mentioned before, my name is Chris, and I'm the student at the Faculty of Physics at the University of Warsaw. And I have a pleasure to give lectures about quantum computing during this QBronze course. At the beginning, I want to mention that if you have any questions during the lectures, just feel free to interrupt me and ask. There's no problem. You can also write your questions in the chat. But I really want you to understand some basic topics And I really want you to, I really want to spend more time covering the basics rather than skipping some really important info and jumping to topics and you don't understand anything. So if you feel lost, just ask a question and I will try to answer it and review the topic once again. So during the first lecture, I will try to bring you the basics of quantum physics and especially review some quantum physics experiments that led to the revolution of quantum physics and quantum computing. Then I'll talk about a little bit about linear algebra and how to manipulate on vectors, how to multiply a matrix, or how to solve for an eigenvalue and eigenvector, because we will then use these concepts tomorrow with basics of quantum gates. And but last but not least, I'll talk about basics of probabilistic systems, which will be topic of today's notebooks. So first, I would like to talk to you about the Stern-Gerlach experiment. And in this experiment, the researchers took a magnetic field, and they tried to push the atoms through the magnetic field. And what they found, I'll try to paste the picture here. And what they found that the atoms, the silver atoms, which have the property called spin, and you can think of it, this is my favorite explanation. I heard this from the professor at the University at the lectures. He said that spin is like, imagine a ball that is spinning, but it's not a ball and it's not spinning. So that's how sometimes quantum can be weird. So you can imagine an atom as a ball with a like arrow, which represents the spin. And the amount, the researchers thought that the amount this atom should, the magnetic field should deflect the atom should be linear, because the field can be, let's say this is the direction of the magnetic field. And so if the atom is aligned with magnetic field, then it should go here. If it's anti-aligned with magnetic field, it should go right here. But if it's like in the middle, the researchers thought the atom should land somewhere here. But it's actually not the case. It turned out that the spin is a discrete property. It's quantized. They only observed half of the atoms to go here and half of the atoms to go here. And this is a quite important experiment because it will be easier for us to then understand how qubit works. And we could imagine the qubit as an atom with a spin aligned or anti-aligned, and I will talk to you about it a little bit later. Second experiment is the double slit experiment, which shows the particle wave duality of nature. And in this setup, we have a slit, two slits, and I will try to paste the graphic, appropriate graphic that describes this phenomenon. So when we have, oh, I'm sorry. Okay, so when we have a light source or a wave source, you can actually also observe it on the waves on the water. You can see that that each slit generates a new waveform. And at the screen, we can see the interference of both waves. But what's actually interesting is that when you take electrons, which, as I said, you may think of them as little balls, the things start to become a little weird. Because you might expect that if you throw a ball on the on such a experimental setup, you would obtain two spots here and here where the electrons should bounce. But actually, we also observe an interference pattern, just like in the case of the waves. And you can actually confirm that the electron is passing through only one hole if you try to place the detector right after the slit. Then you can see that half of the electrons go through the upper slit and half of the electrons go through the lower slit. But when they are able to, when the single electron has more path, then it's like means there's a 0.5% probability that it went through the upper and lower slit. And that's why it creates an interference pattern. And we can say that the electron is in the superposition of going through the upper and through the lower slit. And the concept of superposition will be discussed in the next lectures. And it is quite important in case of quantum computing and quantum physics. And the last experiment is the interferometer. Which consists of a beam splitter, mirrors, and detectors. And actually, if you try to, here we have the source of photons. We can represent it as a box here. And if you try to shoot the photons on the half transmitting glass, then half of the photons should be able to pass and half of them should be able to go through. And you can check this by placing detectors. And you can prepare a single photon emitter so that you're sure that only single photons are passing through that screen splitter. And you can verify this, that 50% of the photons go through this way to this detector, and 50% also goes to this detector. But you can try to then focus both beams at a single point to another beam splitter. And actually, you can, and now I want you to give me suggestions. What would you expect from this experiment, as I have told you that half of them go for this one? Any suggestions? I really depend on your interaction here. What would you think would happen to, how many photons would this detector measure? Any ideas?
Maybe only one detector will measure photons.
Yes, that's true. Here's the answer from the chat that 50% will go through. This.
Krzysztof, sorry for interruption. Could you please check if you can maybe approve people waiting, because now I gave you gave you the host, right?
How do I do that?
Yes.
I'm not sure.
Okay, you can check the list of people. Yes.
No, I'm sorry.
Yeah,
okay.
sorry. Okay.
Yes. Now everyone should be able to join.
Okay, good.
Okay, so actually Dominika was right, and every photon will enter in, for example, this detector, all the photons. Why is that? This is because of the interference I talked about earlier. And actually, this was very known to physicists for like 200 years. It's not something revolutionary, that the waves first split and they interfere with each other to be able to interfere and be detected only by one detector. But if you that's in case when there are many photons present. But what actually happens to single photon? I mean, if single photon goes here, right? And we can also check place detector after it has passed through the beam splitter, that actually half of the photons are here and half of the photons land here. But when we combine the both paths, it turns out that the photon can land only in this detector. And it's really interesting because now you think that, well, the photon has to somehow pass through both paths at the same time. But when we place detectors, actually there's only one photon we measure. So that's really strange behavior of quantum physics, and that's why many researchers, including Einstein and inventors of the quantum physics, they couldn't believe that the word is actually actually how it works. So yeah, I've covered the basics of quantum physics experiments. I hope to bring you more the world of quantum physics. Do you have any questions now regarding those experiments? Okay, if not, then I will try to move to the basics.
Excuse me.
Yes. Yes.
Why are all of the photons going to the detector 1, not detector 2?
I mean, it depends on the experimental setup. It could also be like detector 1, but the reason they all land in in one detector is because of the interference, as I said earlier. So you could imagine like this beam splitter is actually like a plate here. And when the wave bounces from here, right? We can imagine like wave traveling here. But now the wave that is passing through has to travel some more distance in this different material with different speed. Now it has a different phase. It's actually the waves traveling here, you could imagine, is something like this, and the wave traveling here is something like this. So because of this phase kickback, we could say, it turns out that the phase, in this case, the phase of the waves, two waves, are something like this. So the wave coming from this direction has a phase like this, and the wave coming from this direction has a phase like this. And because of the superposition of waves, they both cancel each other out. So like the trough gets to a peak and a peak gets to a trough. And then by adding those two waves, the resulting is that we don't have any wave formed. But in this example, the wave coming from upper branch, we can like say it's something like this, but the wave from the lower branch, because of this phase kickback, is something like this. And now we have like constructive interference. So now the peaks and troughs of both waves add up to even a larger wave. So that's
Okay, thank you.
an intuition how you might think of this behavior, that all the photons land in one detector. But it's actually these are waves, right? So when we have many photons, we can say they are wave. But if we have like one particle, then how can we describe it and how can we explain this phenomenon if we have only one photon? That's a very interesting question. Yes. So now I'll try to go to basics of linear algebra. And the linear algebra mainly relies on vectors, which we can be represent in columns with some entries, example 1 and 0, and for example 0, 1. And we can represent vectors on a 2D plane if we say that this is an x coordinator and this is the y coordinator. So here will be our vector, which is this one. Here we have, of course, x and y. And here will be our vector, which is this one. And a very important concept regarding vectors is the dot product. So the dot product between two vectors is the product of A times C plus B times D. And this is a number. We get a number here, some float, for example. And what this actually means is that we can check whether two vectors are perpendicular to each other, and perpendicular in the language of mathematics means orthogonal, or not. Let's see how these two vectors behave. And maybe I'll also try to ask you a question. Please raise your hand if you had any courses of linear algebra during your studies or even before, because then I will have the basic understanding of how many people are new to maths here. And so please raise your hand if you have been attended a linear algebra course. Okay, I can see that actually not many people. And if those topics are very familiar to you about linear algebra, then you can feel free to skip or come back later. I will focus more on the linear algebra because I see this is a new topic, and actually quantum computing is based on the linear algebra. And if you are able to understand it, the other concepts in quantum computing will become easier to you. So let's go back to the concept of dot product. You can visualize the dot product says how much the vectors are aligned with each other. So now we will try to do the dot product of those two vectors, which is 1, 0 and 0, 1. And this will be 1 times 0 plus 0 times 1. And the result is 0. This is because those two vectors are perpendicular to each other. And if they are, the dot product will always be 0. And now let's try to see what is the dot product of some vector 1.5 and 1.5. So you can also think of the dot product as the projecting the one vector on the other, and they're multiplying both weights of those vectors. So actually, I think it will be easier to calculate the 1 over square root of 2 vectors. So we have 1 over square root of 2 and 1 over square root of 2. And let's see with the vector 1, 0, what we'll get. And as you can probably see by now, you will get the result is 1 over square root of 2. This is because we only get the length of the component of this of the x component of this vector, and we multiply by the length of the other vector, and the length of the other vector is 1. And here also comes the concept of the length of the vector. To calculate the length of the vector, we simply take the dot product of the vector itself. So to calculate the length of, let's say, the vector 1, 0, we take the dot product of this vector with itself, and we get a 1. And when we get the length of the vector equal to 1, it means that the vector is normalized. We say that if the vector has a length of 1, the vector is normalized. And you can also take those two vectors as the basis. So you can construct any vector from the basis vectors. Let's see how the vector like 3 and 2, we can then represent them as 3 times 1, 0 plus 2 times 0, 1. And you can see that in this case, the multiplication works like that the multiplication of vectors means that we multiply this number with every entry in the vector, and by adding vectors, we mean adding the components of those vectors. CD, then the resulting vector is A plus C and B plus D. Right, now when we have this intuition, we can see that this vector can be decomposed to the 3 times the basis vector and 2 times the other basis vector. And those vectors, as I said, are called the basis vectors because they form a basis. And actually, you can choose any two vectors to be the basis vector. So these are basis vectors. So as I said, the concepts of basis vectors are we can combine two vectors to get any vector in our two-dimensional space. So in quantum computing, it's very useful to choose an orthonormal basis. Orthonormal basis means that both vectors, the basis vectors, are both vectors have length 1 or are unit vectors, and which means they have length of 1, and they are perpendicular to each other. Which means that they have a dot product equal to 0. And this will be very useful in our calculations, because then many terms, because of the orthonormal basis, the many terms can be cancelled out. Now I want to introduce you to the notion of bracket notation, which is very useful in quantum computing because it simplifies many calculations, and we will be using this notation a lot. So in this notation, we have what's called a cat. And in quantum computing, we will say that, for example, the cat 0 will be defined as the vector 1, 0. And the cat 1 will be defined as also vector 1, will be defined as vector 0, 1. And actually, physicists like to put very different objects into those cats to represent vectors. For example, in this Stern-Gerlach experiment we had previously, this experiment here, actually the physicists would say that the atom aligned with the magnetic field they will try to represent it like this, and we can also say that it's like a 1, 0 1, 0 vector, and the anti-aligned spin with the magnetic field can be represented as 0, 1 in the case of our vectors. Yeah, but these are called cats. But we also have the bras, which are a conjugate vectors. And it simply means that we try to like flat those vectors and try to lay them down. And I will then try to convince you that this is a very convenient way. So if we have the bra and cat next to each other, this means we have a dot product. This is a dot product between this covector and a vector. And we multiply them simply element by element, like in the dot product. This is, of course, a little bit simplification, what I'm saying right now, because actually the dot product in like strict mathematical way should be between a covector from the dual space and a vector. But for now, it will be just fine to think of dot product of two vectors as multiplying each element with each other. And now we have 1 plus 0, which is equal to 1. And this is also what we confirmed here, that the length of our vector is 1. We can also do the same thing for our 1 vector, which will be also 1. And the dot product of 0 and 1 will be, do you know? Any suggestions? Will be any brave? 0. Yeah, I can see from the
Zero.
chat. Yes. I can see from the chat. Yes, this will be 0. Exactly. So, but we can also place the bras and cats in different combination, which will be, for example, 0 and 0. And this will be like shown as something like this. 1, 0. And this will form a matrix. So now we have a matrix that is which entries should look like this. And a matrix of ones should look like 0, 1 here, and 1, I'm sorry, 0, 1 here. Now the matrix should look like 0, 0, 0, 1. Exactly. And the way that's very convenient to use this notation is that you can combine different bras and cats together. So actually, this operator here will only retrieve us the vector with its component. So if I try to like write something like this, then the resulting thing is that, and also it's very important that the operators in linear algebra are not necessarily interchangeable, so you cannot place the change in the order, but there are a few exceptions. I will talk about them. But they are, you can choose the order of operations. So you can first calculate this and then apply this operator, or you could first calculate this and then do whatever you want with this one. So actually, we know that this is a dot product and we'll try to calculate it. We know we calculated before, this is equal to 1. So the resulting cat of this operation is actually 0 from here. because this is 1. And you can, in case of the numbers, you can place them in whatever order you want, because there are numbers. The multiplication of numbers is interchangeable, but the multiplication of matrices is not interchangeable. So now I will talk to you about how to multiply both two matrices. Bracket is, there's a question, bracket is dot product and cat bra cross product, right? Yes, that's right. This is exactly what I meant. So to multiply two matrices, this is really a quick introduction. C, D, E, F, G, H. You take the, I will try to use colors for it to be easier. You take kind of a dot product between two vectors, and then I get out of the colors, but with a specific order of computation. I'll try to do something like this. So actually, the resulting matrix is A times E plus B times G. And the second entry will be C times E plus D times, I'm sorry, plus D times G, right? Next, we'll have the entry A times F plus B times H. And the last entry will be C times F plus G, I'm sorry, D times H, right? Okay. Do you have any questions by far?
Can you please explain it once again?
Explain what once again? Could you repeat
The
your
last
question?
between A, B, C, D, E, G, and H, the multiplication.
How does this work? This here.
Yeah. Yes.
I mean, it's just the way, it's just a rule. I mean, I'm not, I don't think I'm able to explain you deeply why this is so, but this is how mathematicians that came up with linear algebra, how they define this operator. Because for example, like, you know what is 2 plus 2, right? Because you're told from the elementary school that this is addition, and you know how to work with additions. But actually, mathematicians had to come up with this symbol and what this symbol means. And this is exactly the same as with matrices. They had to come up with how those matrices work. You can think of them, why this is so, as trying to multiply a matrix by a vector. For example, like matrix A times matrix B with a vector V. And to multiply a matrix by a vector, we have A, B, C, D, with vectors, example, A, B, C, D, E, F. So in case of vectors, it works like the first entry is A times E plus B times F. And the second entry is C times E plus D times F. Why this is so? You can think of the first two elements are saying where the basis vectors, so where this vector lands, let's call them like the x vectors and the y unit vectors. So here this gives you the coordinates where the x vector lands. So the x vector was this one, and where the y vector lands. So this was this was our vector. So you can imagine it on the plane and see that this vector 0 goes to some place with coordinates a, c, and the vector 1 goes somewhere with the coordinates b, d. This was kind of a long introduction, but you should be able to see that this operation should be the same as first multiplying a times b, and then applying the resultant then multiplying the result by the vector v. And this is well, the intuition, how you might think of this rule, that this equality must be always true, and that's why this rule applies for the multiplication of matrices. Any more questions so far before we move on to another concepts of math? Okay, if not, then I will go to the tensor product, which is also very important. So the tensor product of two vectors this is a symbol for the tensor product, is actually like we can think of it as like trying to put one vector in another. So we in the case of the tensor product, we put this vector in front of the 1, and we put this vector in front of 0. So the resultant operation should be something like 1, 0 times 1 and 1, 0 times 0. And actually, this gives us, instead of the two-dimensional vector, this operation gives us four-dimensional vector. And now it would be hard to draw, of course, the four-dimensional vector, but the entries will be something like this. You can also try the same operation with, for example, 1 and 0 vector. And in that case, we should get 0, 1 times 1, 0, which will be 0, 1 times 1, and 0, 1 times 0. And the resultant vector will be 0, 1, 0, this is 0, not 6, 0, 0. So actually, with the case of our unit vectors, the resultant tensor is also a unit vector, but for a four-dimensional space. So the other two unit vectors in this four-dimensional space would be 0, 0, 1, 0, which is the tensor of, should be the tensor of 0 times 1. And the other should be 0, 0, 0, 1, which is the result of multiplying 1 tensor ket1. Okay, and keep in mind, because I remember that there is one question about those tensor products and quantum and bits in the notebooks. All right, I think that we can leave eigenvectors and eigenvalues for tomorrow, because we will try to get the eigenvectors and eigenvalues of the basic gates, quantum gates. And now I will try to cover some basics of probabilistic system, because this is the main topic of today's notebooks. So probabilistic systems. So actually, as I mentioned before, those experiments are very based on probability. So in the case of our experiment with photons, we have 50-50% probability that the photon will get through that we have a 50-50% probability that a photon will be reflected or it can pass through. And that's why behind all those quantum computing concepts, we can measure probability. We are not able to measure anything else than statistical probability of a system. So now let's review the classical bits and classical operators, and then I will try to move on to 2 bits and 2 bits of 2-bit operators, and then on those will be like the basic of for tomorrow's lecture, which we will then start building intuition about qubits and gates. So in case of the classical bits, the bit can be either in the state 0 or in the state 1, And we can define 4 functions that manipulate those bits. So we can have a function that's always 1. So no matter what bit in case of this function, no matter what is the input, the output will be always 1. This is a function, this is the function constant 1. We can also have a function, constant function, but which output will be always 0. And 0 gets transformed to 0, and 1 gets also transformed to 0. We can have a not function, which flips the bit. So the 0 transforms to 0, and 1 transforms to, 0 transforms to 1, and 1 transforms to 0. And the identity operator, and the identity sometimes is written as like 1 with another bar. And this also represents the identity matrix. This is a simplified identity matrix, and actually you can verify that identity matrix doesn't change the value of the vector, because this is for example, like some vector, say B. The result of this operator is still A and B, and as a homework you can try to calculate it. So in the identity case, the 1 transforms to 1, and 0 gets transformed to 0. So in the case of the notebooks, it's actually called a coin flipping game. So you can think of the 0 as heads and 1 as tails. And we can also try to assign a value to this assign a vector to this bit 0. So we can have it as 0, 1, and we can assign a vector of this 1 as 0, 1. And then those operators, we can write those as a matrices. So actually a constant 1 would have something like this. And you can check that no matter what the input is, whether it's a 0 or 1. The output is 1, and this is 0, 0, so 0. And in the case of, I'm sorry, this is actually a 1 gate, not a 0 gate. So it should be 0, 0, and 1, 1. So when we calculate, this is 0, and here gets 1, which is equal to our head, our tail, I'm sorry. And the same here goes for the other bit. So 0, 1 will also be 0, 0. This is 0. This is 0 and 1 plus 1. This is 1, which is equal to tail. And we can also try to represent the not operator. As I said before, the 1 is like the identity matrix. So this is really simple. It doesn't change the result. But the not operator is quite interesting, because here we have 0 on the diagonal. Here we have 1. Those terms are called on the diagonal terms. That's also quite interesting. So let's try to verify and calculate what this operator does to our heads. So this operator gives, after the multiplication, which is this and this, plus gives us 1 here, and a 0 times 1, which is 0, and 0 times 1, which is also 0, gives us 1 and 0. So the heads actually are transformed by the operator not, are transformed to tails. And by analogy, you can also verify that the tails are transformed to heads. But what if we have a biased coin? So biased coin. So actually, what I mean, let's frame it differently. Let's now try to reformulate our problem as a coin toss problem. So when we have a fair coin, we have a 50-50% probability that if we have at the beginning tails, this will result in heads, and a 50-50% probability that the heads will result in tails, or it will stay the same. So let's try to see what this matrix does to our heads. Heads was 0, 1, 0. So after multiplying this, we obtain 0.5 and also 0.5. So this means, or we can also say that this is 0.5 times 1, 0, or plus 0.5 times 0, 1, which is 0.5 heads plus 0.5 tails. And in this example, we have 50-50% probability of obtaining heads and tails. So we can either obtain heads or tails with the same probability, which is 0.5. And actually, you can verify that this is the same for the tails, which is 1, 0. And the resultant vector should also be 0.5 and 0.5. But now, what if we have also very important note is that the values in the column should add up to 1. This is because a probability we cannot have a probability like 120%. We can only have 100%, so it's certain. So the columns, so the values in those columns should add up to 1. Now let's try to think about a biased coin. So now we don't have a 50-50 chance of probability, but for example, 0.7 times we would obtain tails, and 0.7 3 times we will obtain heads. So I'll try to formulate my question as something like this. So now the probabilities of obtaining those two outcomes are not the same. They're different. So what happens now, if we like try to get our heads, then the result will be 0.7 and 0.3. And we can try to come up with a different scenario where we start with when we start with and here we start with heads, right? These are heads. We start with heads. We try to flip the heads. I'm sorry, I hear a mistake. And we obtain a probability of 0.7 probability of obtaining heads and 0.3 probability of obtaining tails. Now let's try very similar but slightly different scenario. So we'll start with, now we start to flip a, we had heads, now we start to flip a tail. So we start with a tail, and the result is also 0.7 probability of heads and 0.3 probability of tails. Now try to imagine a different coin that the result depends on whether it's a tail or whether you start with a head or whether you start with a tail. So let's say we have a coin that each time you start with heads, you will get tails. And this is actually our NOT operator, right? Every time you start with the heads, we'll come up with tails. And vice versa. Every time you start with a tails, you end up with heads. And you can also think of a different scenario where the coin also itself is biased. And for example, when you start with heads 0.3, 0.7, when you start with heads, you have a 0.7% probability that it will stay heads. But in other scenario, when you start flipping the coin with tails, you will have not a 0.7 probability of obtaining heads, but also 0.7 probability of obtaining tails. And I will just try to make sure I'm not mistaken. I'm not. It's correct. So it's this is something you don't observe in normally in real world, but this intuition may be very, very helpful for tomorrow's lecture to understand the basics of quantum gates and quantum probability. Do you have any question so far?
Maybe a question about interpretation of the columns in the matrix, you know, how would you say what's the column in the matrix?
Okay. So once again, I will revert back to the example with this map. So you can try to represent, for example, let's take this matrix here. So as you can see in this scenario, we can also rewrite
because if I may say, when you said something like this is like the state 0 becoming state 1, you know, like when we go from the up of the column down to the second row, yes, that's
Okay.
how you it's like a transition, yes, or something
Yes,
like
yes,
this.
yes. So once again, if we have a matrix like this, or I will even make a simple matrix, for example, like 2, 3, let's say, and minus 2 minus 3. We'll see how this goes. With A and B. And you can rewrite the same thing as I need a little bit of as when we multiply vectors, it's 2 times A minus 3B. And at the bottom, we will get 3A. I'm sorry.
No, there's
3A minus 3B, and here's minus 2B. Sorry. Here's 2 minus 3A minus 3B. And we can also divide this as 2, 3 times A plus minus 2 minus 3B. And when we have the first basis vectors of like 0 and 1, this vector here is 1, 0, because the x coordinate of this is 1 and the y coordinate is 0. And this vector, so maybe I'll use the color. And the vector in the y direction is 0, 1. So in case of our vector, like 1, 0, we can say that if A is equal to 1 and B is equal to 0, then we can say that this vector here gets transformed to the place 3, 2, which is, for example, 1, 2, 3, 1, 2, 3, which is somewhere here. So we can think of this as of the columns in the matrix of where the x vector lands and where the y vector lands, because of those operations I made here. I will also try to draw the y vector. So now if the A is 0 and B is 1, which is in the case of our another unit vector, we would see that this vector lands in minus 2, minus 3, because B is 1. So it's something like minus 2, minus 2, minus 3, 1, 2, 3. So it's something like this. Okay. So once again, in the case of this representation in the plane, the first column says you where the x vector lands, which is 2 and 3. I'm sorry, I made a mistake here. Which is 2 steps in the x direction and 3 steps in the y direction. And where the second unit vector lands, which is minus 2 and minus 3. Have I answered your question correctly, or do you have any more doubts?
Yeah, okay, thank you.
Thank you. So now we will try to get to the 2 coins probabilistic state. So in the case of the 2 coins, and usually when you think about coins, they're they're the same coins. I mean, you are not able to distinguish between them. But in our case, we should be able to mark the coin with number 1 and 2. So that now the space of all possible outcomes of a coin are heads, 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 tails, tails, heads, and tails, tails. So now you need a 4-dimensional space to be able to represent all those 4 different possible scenarios. So we will try to now write the basis vectors of those 2 states, which are 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And as you can see, this very resembles the tensor product we discussed earlier. And we can now go a little bit to 2 coins operators. And let's say we have a very special machine, actually a black box, that takes as an input 2 coins. Coin 1 and coin 2. And the output of the coin 2 depends on the output of coin 1. So if the coin 1 is heads, then you should do nothing to the second bit, to the second coin. But our machine is such that if on the first coin is tails, the machine says to the second coin, flip. And we can represent this also as a matrix with now 16 entries. Here we have 1, 1, 0, 0, 1, 0, 1, 1, and all of the rest are zeros. And you can think of this matrix by dividing it into 4 parts. So the first part, as you can see, is the identity matrix. This is a small 2x2 matrix. The other ones are 0, 0, and this is a not matrix. And it's also very useful in linear algebra to divide matrices in other forms. So now you can see how this works. So the first one, if the first qubit is heads, the matrix says do nothing to the second qubit. It should stay the same. But in case of the tails, the matrix says flip it, or apply a not operator. And this gate is very important in the case of quantum computing. It's called a controlled not gate, and we will discuss it in detail tomorrow. But now I give you the intuition that such gates are possible, that you have a coin, and depending on the value of the first coin, the second coin should flip, or its value should stay the same. I think that from my side, this is it for tomorrow. For today, I'm sorry. Do you have any questions? Maybe. So if not, then I think I can thank you for today, and very kind you were listening. And I hope that you now have a 1.5 hour to complete the notebooks. And if you have any questions during the notebooks, I will be able to answer them on Discord. So feel free to ask, and don't hesitate. And we will be with other mentors available by 9 o'clock UTC +2. So you have 1.5 hour to complete your notebooks. I see a question, and you raised your hand. Łukasz. I see a hand from Łukasz. Or is it? just from before. I assume it's from before. I see some chats. Okay, the sum must be 1 from Valid Shora. Is now a question, is tails 1, 0 or 0, 1? I defined it here. It's 1, 0 and tails is 0, 1. But in case of the notebooks, it may differ. I mean, I'm not sure how they represent it there. It's how I understand those concepts and try to give you more of an intuition how to deal with linear algebra, because at the first it might appear quite strange, but it's really simple. And once you understand those concepts and topics, the quantum computing will be much easier for you, and you will be able to learn much faster. Which notebooks should we complete? The notebooks are listed in the agenda, and these are, I will give you the answer, but I will need to find it for a second. The notebooks are classical probabilists. I'm sorry. This. The notebooks are definitely listed in the well, course materials, and I will try to really quickly find this for you, so you're not missed. Oh yeah, check the agenda. Oh yeah, thank you. Here's the link. Yes, and the notebooks for complete are 1-bit, coin flipping game, probabilistic states, probabilistic operators, two probabilistic bits, correlation, and operators on multiple bits. So really, really quickly, I will give you in 5 minutes about correlation. So correlation means that if we have that each time we flip 2 coins, we will also always have either both tails or either both heads. And you can check this by, for example, a vector, something like this, 0, 0, 0, 0.5. So each time, this is like 0.5, which is 1, 0, 0, 0, plus 0.5, 0, 1, sorry, 0, 0, 0, 1. So each time which this represents heads, and this represents tails. So each time you flip this coin, it happens, it's such a way that they are correlated with each other. They'll, like, in quantum computing, we would say that they're entangled with each other, but we will cover this concept tomorrow. So each time you flip 2 coins, they are either heads or either 2 tails. Yes. Why we are using tensor product of H, and other terms? I don't understand the question really. How to pronounce your name correctly? Shreyas? Okay, so I'll why do we use tensor product? Because now we are dealing with 2 coins, and we have 2 different outputs. Remember that those coins are labeled, so we can distinguish between 2 coins. So normally in the case of 2 coins, many people think that heads and like the heads and tails from one coin and tails and heads from the other coin are the same scenarios. So you have actually the half probability of obtaining this result. But in our case, we distinguish between those two scenarios, because we can label which coin was which and whether it landed as heads or as tails. And we use tensor product because it's like easier to to describe it in terms of vectors. So I don't know if I answered your question correctly, or do you have still any doubts? Okay, if not, then thank you very much for today, and feel free to ask questions if you have any problems with notebooks. We have to submit any of the notebooks once we solve them, or any email. I believe you don't have to submit the notebooks. They're for your learning journey only. But you can confirm it with Pavel. In order to obtain a certificate, you need to do your homework in Canvas. But homework in Canvas is like ABCD questions, I believe, or you need to calculate something, but you don't need to post your notebooks.
I should
Yes.
have a question.
Yes.
When we'll get Canvas invitation or QBronze assignments?
I think that Pavel will send this in a days. So in
All right.
short time, you will receive the link to the homeworks, and the homeworks will be available by 13 October. So you can also complete those homeworks after the course.
Yeah, sure. Thank you.
No problem. So yeah, now I will switch to Discord, and if you have any questions, you can hop to the voice channel, and I will try to answer your questions if there are any. So thank you, and see you tomorrow.